The angle we're going to make is 3 degrees. We're going to pull the lever down, so it's going to be clockwise from the horizontal. And originally, the wire is 600 millimeters long, or 0.6 meters. So the L naught, 0.6 meters. We want the normal strain, epsilon BD. In this section, we're not looking at free body diagrams. We're not worrying right now about the forces and the stresses. Once we start looking at stresses again in the next slides, then we need those again. Really, we're just drawing the geometry for right now. And then when we integrate the stresses and the strains, we'll need geometry pictures and free body diagrams to be able to solve them. I want to first draw just a diagram of what's the original orientation of this. So when the bar is horizontal, what does everything look like? We know that that wire was 600, or 0.6 meters. And originally, BD is at a 45-degree angle. This is a right angle with the wall, so we have a 45, 45, 90 triangle. Knowing the hypotenuse is 600 millimeters, we can compute what the other two legs are in the original orientation. Actually, in this one, I did in my notes stick everything in millimeters. Once we move it, now our triangle is going to look a little bit different. Point D remains where it is. It's still anchored to that pin that's connected to the wall. The wall is not moving. Point A is not going to move either. So when we pull that lever, what does change? Right, what was the hypotenuse, BD, is going to change. It's going to now be able to stretch. Bar ABC cannot stretch because we're going to consider it a rigid lever arm. Rigid means it's non-deformable. It's not going to change length. It's not going to change shape. However, the wire is going to be deformable. So what we can translate this to is that point B is no longer where it once was. It's now going to move down, which I'll call B prime. In picture 2, what is known and what is unknown in picture number 2, now that we've pulled the lever down and point B has now moved? What's that? The angle, which angle? What is this angle going to be? Or is that a known or an unknown, I guess? Right, we can no longer say 45 degrees there. Yeah.
We know what side DA and side AB are.
Right, DA has not changed. It's still 424 millimeters.
And AB prime is not changed.
Right, and the rigid lever arm has changed its orientation, or it's still rigid. It's still collinear from A, B, and C. However, it's now angled down. But the measurement between A and B prime remains the same. The bar did not lengthen. The bar did not contract. Yeah.
Is the angle at A 93 degrees?
Right, and we know this is 93 degrees. It was originally 90. We rotated this down by 3 degrees from the horizontal, so in its entirety, it's a 93-degree angle. Those are the things we know. We don't know the length right now, or it's not given to us what B prime D is, because the wire is deformable. It can stretch, so it's not necessarily 600 millimeters. Let's go to the equations, and then we can come back and see what are we trying to find, or what do we need to get there. We need to find the strain in BD. How can we find what the strain in BD is? Even if we don't have numbers right now, conceptually, what do we need to know to calculate what that average normal strain is? First, conceptually, it's the loaded length minus the unloaded length divided by the unloaded length. Is now, we don't know, I'll just call it L prime for right now. It was originally 600 millimeters long, and we divide that by 600 millimeters. As long as this is in millimeters, then my units are consistent. So either everything in millimeters or everything in meters. So to find this, I need to find L prime. How can I find L prime based on my diagrams? So I'm actually going to use law of cosines to solve this one, but you're right, you could use law of sines. Law of sines is fine to use if you're looking for lengths. I really don't like using law of sines if I'm looking for angle measures, though. So I know, using law of cosines, or your favorite law of trigonometry, the L prime is going to be 424 squared plus 424 squared minus 2 times 424 times 424, or 424 squared, times cosine of the opposite angle to L prime, which we know is 93 degrees. So again, law of cosine c squared equals a squared plus b squared minus 2ac, minus 2ab cosine of angle C. In law of cosines, the only thing we don't know is the L prime. We know that it has to be positive, though, since it's a physical measurement. We find using law of cosines, the new length is 620 millimeters. Now we can put that into equation number 1, and we can find that the normal strain, BD, will be 20 over 600, which is going to be 33.3 times 10 to the negative 3 millimeters per millimeter.